Thanks for not walking out, right? This one is from 2018, and it's about discrimination aware channel pruning, which is discrimination aware, not of people, but of channels and the convolutional neural network. And then based on this paper, a company called Tencent came out with a tool called Pocket Flow. How many of you guys have used it so far? Okay, it's super important that you guys know about this tool. The only thing that's a little shady about it is that it operates a lot by fetching models from an API, and Tencent is a giant conglomerate, so I have no clue what that API is serving. So I can't promise you the integrity of what's behind that, but that doesn't stop me from using it. You guys should use it. So we'll talk about Pocket Flow. I strongly recommend using it. It works great. So first, because I saw one act of excellent shameless self-promotion today, how can I resist but doing the same? So we like to think that we're building the world's greatest development tools, including a world-class tool for interactive model training. Morten in the front row has the honor or unhappiness or both of helping us debug it by being one of our brave beta testers, and you guys can too. If you go to app.meeshkan.com, I think you can attest that we're a nice team, we don't bite, and we listen to feedback.
You haven't beaten me yet, but
nah.
we'll see.
Yeah, sure, I haven't. So yeah, check it out. Lots of great machine learning projects, including research collaborations with NVIDIA and Northeastern University. We're based in Helsinki, remote work is possible, and just ping me at mike@meeshkan.com. That is the company. So you have a quarter of the company here tonight. That's pretty, that's a lot, right? So there you go. Now moving on to more important things. So actually, because you guys don't have computers, it's irrelevant, but this is relevant. So paper overview number 1. Deep compression, compressing deep neural networks with pruning, train quantization, and Huffman coding. So the main thing I want to talk about today is train quantization. Pruning is kind of it will happen automatically if you use Pocket Flow. But train quantization, Pocket Flow doesn't really use it, and it's a super cool method. It's the one that I'm most excited about, actually, of all these, but we'll get to all of them. So, man, I thought I was awesome with the whole clicker thing, but I'm not that hot. Let's maybe make it full screen.
Let's do full screen.
Yeah, let's see.
You can change the mode to get rid of this thing on the left.
Yeah.
It's Linux, so probably no.
Yeah. If any of you guys want to patch the kernel really quick to make that possible.
100%. Do 100% there.
I think there's a fit to screen or something. Fit.
Fit of page.
With?
Page.
And you can crease the X one there. There is X there.
To the left?
And this menu.
How many machine learning engineers does it take?
Have we tried F as well?
Jim,
Okay.
ja, det är X on the try control L.
L.
Control L.
Nope.
No.
But why is it?
Now it's working.
Yeah, but why is it jumping? It should be like.
Yeah.
Try to fit page
F11.
with or something. Magic.
Okay, I'll try it with the clicker and just see if
Yeah,
that.
try with the clicker now. See?
Okay. Well,
Anything happening?
that was underwhelming. No. Okay, great.
I think this looks better, right?
Okay, I'm cautiously optimistic.
Oh, sorry, that's me.
Okay.
Try it now.
Sweet.
65.
Yeah.
5% should be perfect.
Yeah. David, want to do machine learning on this? Yeah. If worst comes to worst, of course, I get scrolled down. So, why deep compression? A couple things. One, if you're doing mobile apps, restrictions on app size and mobile app downloads. For those of you who have ever trained like VG16 or something like that, you know that the networks are huge when they come out. Even MobileNet is quite big for a mobile app, and MobileNet is the smallest kind of commercially viable thing that's mass out there in the market. If you guys are using some like Inception or Exception or any of these Ception networks, it's going to be even more. And of course, if you guys are using any of these ResNets, like ResNet 101 in a mobile phone, will just break the mobile phone. So restriction on app size is a big deal for those of you working in apps. But even if you're not, this is the bit that like nobody talks about, and it's totally the elephant in the room. So let me like get to this really quick because it's super, super important. I have no clue why nobody talks about it. So energy consumption. So the real killer is memory access, and nobody thinks about how much energy these things consume. I've seen companies like really struggle because they think they've finished because they've trained the thing, and then it drains the entire phone or the camera or whatever in like a matter of minutes. And it's really bad. So the other thing is that people totally focus on the wrong stuff. They assume somehow that like flops take energy, but no, that's false. So a 32-bit floating edition actually just consumes that much.
Sorry, wouldn't that depend on the platform?
Yes, of course. Yeah, it absolutely is platform dependent. I forget where this benchmark comes from, and it would be irresponsible of me to say that it scales like this on all platforms. But knowing that 75% of statistics are made up on the spot, I will say that yes, it does scale to all platforms. So 32-bit floating add consumes this much. Then cache access from the cache memory. So how many of you guys have done memory I/O with NVIDIA GPUs before? Okay, a couple of you. So NVIDIA has this universal memory access now that makes it a lot easier, but in the bad old days when I started this, they didn't. So they had different levels of cache, and they have this global memory. They also have like a L1 cache. They even have like, if you're really creative with NVIDIA, you could use their GPU shaders, like that are doing shading for graphics, and you can even store memory in there for deep learning. But it's all quite fast. It only takes that. Anything from the RAM, on the other hand, takes like, I mean, you guys are really good at math, so I will let you figure out how many times that is more, but quite a lot, 100 times more than the others. So basically, it's totally ineffective to be copying memory back and forth all the time, and usually multiple copies are happening under the hood, and it's all like abstracted away, and then your phone runs out of battery in an hour. So what this means is that a 1 billion connection neural network at like, let's say 20 frames per second, if you're doing like video processing, like you work at Snapchat, require 12.8 watts just for DRAM access. At which point, like your phone, like if you do deep learning on the airplane, it will like explode, and then the airplane goes down, and then your company goes under because you have to pay for that, right? So you don't want to. It costs. Yeah. Don't do any of that. Then the other thing is time is a huge bottleneck when memory is not cached, and that's really where my company comes into it. So slight, shameless self-plug. We're doing this research project now with CUDA team at NVIDIA and Northeastern University on something called checkpointing. You guys know what checkpointing is, like when you take a model off the GPU and just like save it, you take the checkpoint of the model, right? So checkpointing takes time, and so we're working on zero downtime checkpointing, which essentially requires putting a library between libCUDA and TensorFlow and doing memory management of everything that's written to CUDA, storing it, knowing what memory goes to the GPU, and then saving that all the time so that when you checkpoint, you just save a shadow copy of the memory. RoboElectric for Android works the same way. But if you don't do that, then time is a huge bottleneck when memory is not cached. So in addition to like burning your phone and having an app that takes 200 megabytes, it will also be slow. So like that's what happens if you don't compress your neural networks, right?
Aren't you mixing training and inference now?
No, inference I'm talking. I mean, meaning that inference still needs to copy over to the...
Yeah, but you don't need checkpointing for inference.
No, sorry. So checkpointing is only for training, but I'm saying that the process of checkpointing requires copying memory back from the GPU. Yeah, that's what I meant, but you're absolutely right.
Are you just working with that one hardware platform, or are you interested in other, supposedly AI efficient platforms like GraphCore? Have you thought about that?
Like GraphQL, I mean.
GraphCore.
It's another NVIDIA.
It's another hardware that claims to be 10 to 100 times better than NVIDIA.
The only, I haven't seen it. The only thing I've seen along those lines, but it's made by NVIDIA.
No, it's a competitor.
Is it Oxford?
No,
Cambridge.
they're in Bristol, and they've got Sequoia behind them. They put $50 million into $50 million. But they claim to have a very competitive architecture for this type of.
Interesting. The only one I know is Wave in California. That's I guess, a competitor of that.
But I mean, would this be changing anyhow as we really go to the neural network processor? Then I would assume if you have a specific hardware design, you would have a memory design which fits to that.
I mean, it's
It's
still.
stick and all this stuff.
Yeah. I mean, of course, as hardware gets better and better, some of these problems go away. But still, the size of the model, meaning if you have n weights.
I agree with this.
Yeah. But you're absolutely right that will speed that stuff up. I actually haven't seen that many commercially viable products that do that. Though Nokia develops an AI chip that's like a USB thing that you can put right in.
Intel has a
The Irish one that they acquired. But there's also another one optimized for neural nets in the US as well.
Yeah, maybe that's Wave.
But this is the latest one in GraphCore. There's plenty of information online, and they've got loaded first. And Dell are also going to bring it out on their hardware.
Interesting.
So
I to be honest, I need to check out what those chips do. I mean, I'm curious to see. Is it just that they do like reduce operations or?
they have lots of fast RAM basically.
Okay, excellent. Yeah, I mean, the world would be an exciting and or scary place when those become commercially available for everyone. But I unfortunately, I don't know that much about it. I feel that this problem is still going to be worth solving, even when that day comes around. Even though this bottleneck might not be there, maybe the energy one will be. But of course, the hardware gets into it. Absolutely right. So, network pruning. So, the first thing that I want to talk about, the second paper does this better. So remember, this is back in 2016. And this is kind of, to me, the least interesting algorithm for a variety of reasons, not least of which is that you have to represent things in a sparse matrix, which you can't really do on a GPU, at least not today. So first, train the matrix as you normally would. Then, after it's trained, remove all the connections with small weights under E. So you see that this is not a loss function. I'm not talking about like L2 normalization and the loss function that like pushes the weights down. I'm actually saying find the weights, remove all the ones under a given epsilon, and then at that point you have a dense matrix with lots of zeros, which means it can be turned into a sparse matrix, and that's kind of the way this algorithm works. In order to compress the gradients, what they don't talk about in this paper, though, that I don't really understand, is that when you're running inference on the phone, I don't know if they expand it out to a dense matrix or not. They don't talk about that, but I don't understand how you could do fast inference from a sparse matrix in TensorFlow, at least. I don't know if you guys have ever used the TF sparse libraries before, but they don't work that great. What do you say?
How big is epsilon?
My cop-out answer is as small as you want it to be, but it's I mean, at the end of the day, neural networks have lots of small weights, so it's like an art more than a science. But that's what data scientists are paid the big bucks for, right? For changing it from 0.0001 to 0.002. But I'm not exactly sure. I mean, I can't comment on that. But this is just kind of the algorithm, so it's a good thing to know. Then the important thing is, this is assuming that you've trained it once, but then you retrain with only the connections you've kept. And this is super important, and it's also true in PocketFlow. In fact, PocketFlow only works on networks that have already been trained already, so that's where the two are in common. So the reason that this works, not that surprising, but weights that have a multiplication of 0 are close to the multiplicative identity function. That doesn't surprise any of you guys. So of course, doing a bunch of 0 multiplications doesn't matter. So it doesn't have an impact on the network. So there's many ways to store sparse matrix, and if we were doing more hacking in this room with the, I'll give you guys the GitHub repo in a little bit, but we probably won't get to that much of it. So CSR and CSC. Sorry, I hate when I do this. I forgot to close the parenthesis here. That like annoys me so much. I hope that like I have a neurosis about that, but I hope you guys heard that. So the CSC is also find or just use your favorite matrix tensor package. Like SciPy has like 8 different ways to make a sparse matrix. Then one interesting thing that I learned about at PyImageConf, which was in August this year, which is like a thing for people working with images, that was in San Francisco, is that they're starting to have these domain-specific compression things. Like in order to compress a convolution network, you know that it's going to have a kernel that has a certain size and a certain number of channels. So by knowing the topology of the convolution network, you can have even more compression because you don't need to have like ij of a sparse matrix. You just know you know what the address space is going to be because you know the size of your convolutional neural network. So in extreme cases, that helps too. But the main thing to take away from this is that there's going to be a retraining process involved where you use a sparse matrix. And the sparse matrix can go right in the autograd function, for example, by George.
Yeah, the fourth point, the multiplication of zeros is close to the identity function. Would that mean, for instance, if you have a linear layer, the diagonal elements, then you would actually do the offset to 1 instead of 0? Like if the difference between that element just to be closer to an identity function? Or do we just ignore diagonal elements?
So I mean, identity function in addition, meaning that when you do the reduced sum of everything. Yeah, I apologize for that. Not multiplicative identity. Sorry about that. No, I'm thinking about when you do the dot product. Then of course a bunch of zeros added is just 0. But yeah, that's a really interesting question. Stuff that's close to 1, can you get rid of that too? Of course, if a weight is close to 1, then you can get rid of multiplication as well. I've never seen anybody doing that, but that's a really interesting thing to explore and could be the subject of a paper, like getting rid of the multiplication. But what I will say, as you guys know, is that the reduced sum in a dot product, that is many more layers than the multiplications. Even though there's the same number of multiplications as there are additions, the additions happen sequentially, whereas the multiplications can all happen in parallel. So that's what's also.
I'm not quite sure how useful it is to get rid of the modification because you usually fuse multiply and add on with the platforms. So that's the multiply and add in single cycles. So.
Yeah, I mean it's tough, and it really, so that's a really excellent point. The way, so my cop-out answer, sorry, which, like, I'm going to kind of fake answer your question, saying that like the authors in the paper don't talk about that, but you're absolutely right that is practically true. I don't know if you guys have ever used stuff like PLAT-ML before, but you can use all sorts of operations in there. And yeah, I mean, there's in the case where there's a fused operation, you're probably right that this doesn't have that much.
So if you have a lot of weights that are under epsilon, wouldn't that be a sign that you have a wide network? And then if you just reduce the number of nodes and layers and
True, but this assumes that like it's 3 days before hitting production, you can't retrain it because it took 3 months and you just need to make the thing smaller. But of course, if it's early enough in the process and you have like a histogram that's basically like flat, then I would totally just redesign the network itself. Yeah. Good question. Okay, so that's network pruning, and we'll get a lot more into this when we talk about pocket flow.
Okay.
Yeah.
Another question.
Sure.
Wouldn't that depend, I mean, when multiplying the zeros and the weights, and wouldn't that depend a lot on the activation functions that you had in the names as well? I mean, they behave completely different to zeros and small numbers.
Yeah, although the activation, yeah. I mean, here, at the end of the day, if you have a bunch of additions that are basically close to 0, and they go through like a ReLU, for example, it'll still be 0. Like the activation function won't touch, won't change the zeroicity of that weight for that activation function, I guess. Yeah. Any other questions about network pruning? You guys talk a lot more than Finns. This is really like moves to this country. This is a pleasure. But any other questions about network pruning? So that's the first step. I think they claim to get like a 25% reduction or something like that from network pruning. Knowing that this is made by researchers again, so I'm not sure what hardware they're using or how then
that's conditioned on they actually having a too wide network to start with, and then you can get any kind of reduction that you want.
True. I mean, it's kind of, if you start from a really bad place, then you can always do quite well. But I think they did it on, it was CFAR 10 and so that's another thing actually. I'll say my one like political thing here, which is stop doing benchmarks on CFAR 10 and MNIST in your papers. Because I think that in 10 years, or like anthropologists will look back at our era and be like, those guys are really good at recognizing handwritten digits. But like I think that we could use more diversity in our benchmarking. Anyway, so I'll shut up and move on to the next thing, which is weight quantization. So if you take one thing away from the presentation, aside from the fact that the speaker was drinking during it, it's that weight quantization is by far, I personally think, the most innovative thing in this paper, and it's a pleasure to read and understand, so I want to spend a little bit more time on this. So the first time I tried weight quantization was in this kind of naive word size thing. Does everybody here actually know what word size means? So I see a lot of no's. So let me tell you. So word size in computing is just assume that you have a unit. Like, so a 32-bit float is 32 bits. That's like the word size, right? And the word is the float. So you could also represent it as an unsigned integer or a lot of other things, and that's just the word size. I don't know why it's called word size. I probably wasn't even born at the time that they came up with that term, but that's what it's called, word size. So I naively, when I started doing deep learning, said, oh, 32-bit floats, that's like way too many bits. Why don't we just reduce it to like unsigned integers, have some type of like transfer function in and out of integers, and then do deep learning that way. Terrible idea. It just doesn't really work for a variety of reasons. But the main intuition to get from that is that the same problem comes up in aliasing and audio and image. So do you guys know what aliasing and anti-aliasing is? Have you guys? Yeah, so I see mostly none. So if you just do naive quantization of like rounding down or up to the nearest thing in a word size, then you get aliasing problems in all sorts of ways. Like it introduces noise into the signal. It introduces periodicity where there is none, so it introduces signal into the noise. It actually has both problems. But the main thing to know is that weight quantization does not mean decimating the word size of your neural network. So if you have 32-bit floats, it doesn't cut it to just cut it down to 4 bits and then round everything up or down. Bad idea. You guys are probably like, we knew it was a bad idea. Why did you try it? But I'm just saying. So it's a really bad idea. This creates the same type of aliasing problems you get in image and audio, and you can do a discrete cosine transform of poorly quantized weights to see if they suffer from this problem, the same way that you would do an FFT of an image or audio. You'll physically see the noise introduced by it if you do that. So what's really interesting with them is that they do k-means clustering approach to quantization, and they also do a really interesting idea of initialization of the values that you quantize towards. So let's learn the algorithm because it's pretty easy to implement.
Question, so with, I see people using half precision floats instead of full precision floats.
Yeah.
Would that introduce the same problem?
So do you mean like going down from 64 to 32 or from
Yeah,
32 to
exactly.
60?
From 32 to 16, but still floats.
Interesting. You'll have a...
I mean, I know that Facebook is doing that.
Ah, well, if they are, then that's must be fun.
You NVIDIA Tensor Core are also basically optimized for 16 floats, so they can basically work some vectors of 16 floats. That's very good.
Okay.
But I have
but
paper.
You have problems with it. I don't think that you really get these type of problems. What you get is the problems like vanishing gradients get worse when you have.
Right. But I think they only do it when they do inference. So for training, they say
I mean, I think the point with the TensorFlow, maybe, but
okay. Well, I
I don't know.
no, but that's what I do.
You can train it in 16-bit. You can absolutely train in 16-bit, but it has challenges. There is some article about how to work on the challenges.
Okay, maybe you can do normalize it differently. I mean, multiply everything.
Yeah, that's for more lessons to scale it up to reasonable.
Okay. Do they do that as like the last stage after everything is done? Just out of curiosity, the normalization.
I haven't read the whole thing, but yeah, as it said, I have an article somewhere on the NVIDIA page that's around the challenges of 16 training with 16
Interesting. These guys get it down to 5 bits, which is like madness, but it totally works. So I'll talk about this. I would say like seeing is believing. Like it's a really cool technique and it hasn't been adopted a lot. So I'll go over what it is. It's worth like if you have a pen, paper, or a computer or whatever, just to write it down. It's in the paper too. So it's called weight sharing by scalar quantization and centroids fine tuning. So what does that mean? Let's assume that these are your weights and they're 32-bit floats, right? So assume for a second that you've done some type of k-means clustering algorithm. We'll get how to do that in a second, but let's say that's been done. And we know what the prior is. So let's, here we know that this is our centroid, this, and this, so all those are our centroids, right? So convince yourself that this is blue because this is closest to this weight. So these are weights, right? 16 weights. So this is closest to this centroid, this is closest to this centroid, and so forth and so on. Of course, it's not going to be a uniform distribution because most of them will probably be close to 0. And I don't think it's even uniform here. No, like here you have 3 greens. I feel like I'm playing Twister, but like 5 oranges and so forth and so on. So we'll get on how to initialize these centroids in the beginning, then yeah, after this slide. But for now, just know that's what it is. So here, also convince yourself that this is the index for the centroid. So if this is centroid 3, then this spot corresponds to centroid 3. This spot, the green, corresponds to centroid 0, right? So you see all of the weights get mapped to a given centroid. Okay? So what, and again, this is assuming that you've already done training. So the weights are not just like the crap that you put in the beginning, but they're actually like bona fide weights because you've done a feed forward neural network. So then the really interesting thing, and I had to like do it to see that it works because it's not intuitive to me that it does, is that when you do gradient descent on your refined network, you take all the gradients and you use the same mapping as this is the centroids. Does that make sense so far? So if this is the gradient for this, then you map this all to the same bin. You take them, you add them up, right? So again, convince yourself that this is the sum of this. You multiply that by the learning rate, which here they did a really unoriginal and like, well, the learning rate's 1 essentially, and then subtract it from the centroid. Yeah.
So are the gradients calculated using the compressed centroid
Yes.
or the original?
The centroids.
Oh, okay.
Absolutely. So in the forward propagation, you use the centroids, and the gradients are calculated again from the centroids. Yeah.
So wouldn't the hyperparameter optimization of the number of clusters introduce a huge extra load on the training time?
What would it introduce?
I mean, you need to fix k for cadence.
Yeah.
So how to fix k?
That
would introduce a lot of training time.
Well, the authors of this paper argue kind of backwards that you fix k based on how much you want to compress the network. So of course, the smaller k is, the training time will be way larger. Because I mean, if you only have 2 possible ways it can be, then like good luck training that neural network. But like the
but you also want to keep some kind of performance, right?
Yeah, exactly. However, their argument, which is true, because I've like seeing is believing, I've done it, is that it will take longer to train. I mean, you're going to retrain your neural network, but it winds up getting about the same accuracy as the previous one. I'll show you the stats in a second. It's pretty incredible, actually. At the end of the day, once it's fully trained, meaning that once it's gone into its previous accuracy, your network doesn't take any hit, essentially, because then at that point, you know what the centroids are, and you just kind of plug them back in. So like this becomes 2, this becomes 2, this, and so forth and so on. And gets filled out. Again, one interesting thing that they don't talk about is that even though you're doing gradient compression, at some point there's going to need to be an expansion, right? Or at least there's going to need to be an indexing function so that this reads this. So that indexing function itself might be slow because it might take place on RAM or something like that while it's doing the inference, or you might just expand out a full array like that on your GPU. So there's still problems associated with it, but to me, the crazy part, I don't know about you guys, is the idea that you could just add up the gradients for the things that fall into the bin, multiply them with learning rate, subtract, and it works kind of this. You're shaking your head no.
Yeah, I mean, it sounds incredible.
Yeah, kind of like dropout, right? The first time I found out about that, I was like, nah, that's bullshit. And then it turns out that like, it actually works, right? That's exactly what I thought about this. So it's super cool, yeah.
Where do you get the different learning rates? The different learning rates, because they're not the same, right? So how do you get those?
The different learning rates.
So each cluster, why I understand this wrong, the blue cluster, they have like 0.04 learning rate?
Oh no, that's not the learning rate, sorry, that's the sum.
Ah, okay.
So you add up all the gradients,
Yeah,
so
right, okay.
sum.
Yeah, and then you multiply by the same learning rate.
Exactly, which is 1 in this case. And then subtract and go from there. We haven't talked about how to get these centroids yet in the beginning, how to initialize them. Of course, once you initialize them, then the learning rate kicks in and that's fine, but we'll talk about initialization in a second. You had
Right, so this is all done after you're done training on, like, proof you're done with your original training, and then you do this as the last step.
Exactly.
Yeah.
Exactly, yeah. And it really, like, I think something like 35% smaller on average, just by doing this. So you can see that the bins, the number of bins you have, is the word size, right? So if this all of a sudden got really like romantic with the candelabra. Okay,
I
cool.
don't know what happened with the lights, but maybe it's fine.
Yeah. Yeah. The